Hello, Microtronic fans. I'm happy to show you the second version of my Microtronic bubble LED retro display version, right? So I already showed you the first version, and I've here on the right, that's the first version, in which I made a couple of mistakes in the PCB design. So the biggest one, that the dedicated power switch does not work for the battery, so I had to put in that extra switch only for the battery, which is kind of an ugly hack. And of course that triggered me to basically redo the PCB routing. And so I also put in a proper battery clip holder here, and I didn't see the point of putting the battery clip holder in here, right, because of that ugly hack. I knew it was a temporary version, so I just used double-sided tape to glue in the battery here. Another change I made, so this originally I used the 7805 voltage regulator here, bringing the 9 volt battery voltage down to the 5 volt required for the electronics, for the circuitry and the microcontroller and such. And I noticed that that got pretty hot, that SMD voltage regulator. So I put that heatsink here, which is a Raspberry Pi heatsink. It's just attached with adhesive tape. Basically, it's still wobbly, and I disliked that, right? And I figured, okay, for that, I can still use a conventional 7805 through-hole voltage regulator, which I can then more easily attach a heatsink to, right? So also I put in a reverse voltage protection diode, so if the power supply is plugged in, I do not want the battery to be charged by this, right? And so that's what that diode takes care of. And I corrected another little mistake I made here. You can see that I have a aftermarket patch cable here connected to one of the inputs of the bus driver, basically. And of course that's also fixed here, right? No more cables. In general, I now have my technique basically to use the hot air soldering iron. So all of these chips were now produced soldered using the hot air station and paste, rather than solder wire and the conventional soldering iron. So for this I still used the conventional soldering iron, and I used desoldering wick in order to fix bridges, right? And so I no longer need to do that. I can use my newly acquired hot air station, and I figured out the right amount of soldering paste that's just right to not produce bridges, right, and to have enough solder. So it's a balancing act, and that requires quite a bit of practice and fiddling with the right temperature and the right airflow from the hot air station, things like that. So yeah, then I figured, okay, now I have two of those boards. What can I do with that? And the whole thing is, of course, designed to support input outputs and electronics, right? So here I have a counter integrated circuit connected. It's a Texas Instrument SN74143. It's a simple BCD counter integrated circuit, and a 7-segment display decoder, right, included. So what I'm demonstrating here is that I can load a program which basically drives the counter. Let me load the program from EEPROM at slot number 4. And what that demonstrates is that I can basically send clock pulses into the counter, and it will count to the same number that I'm inputting here. So as you see, I put in a 1 and it counts to 1, and I put in a 8 and it counts to 8 slowly, right? And so you can see that this LED here is basically the clock wire, right? And it's pulsing slowly, but I can also increase the emulation speed, and then it goes much faster, the counting process. And the counter is, of course, powered by 9 volts and ground. So it's connected here to the power pins that I have on the board. So there is the 9 volt from the battery is available. There's also 5 volts available, and there's ground available, right? And so whereas this counter is connected to this board over the outputs, right? So one is the reset line and one is the clock line for programming, for making the counter count. The other board is connected to the 4 digital outputs of the counter, which is just the binary encoding of the current counter value of the digit, right? And it's being read into it's connected to the digital inputs of this board here. So let's write a little program on this one, which then reads the digital value from the wire basically and displays it on the display. So I'm putting in display register 0 on the display, and then this is the data input over the digital inputs into register 0 and go to 0. So it's an endless loop, and all it does is it's constantly scanning the digital ports basically, and the digital input port, and putting the value it reads on the display, right? And you can see that this now correctly mirrors what I'm sending into the counter and the counter value, right? This is 8, so 1, 2, 3, 4, 5, and so on. And it's a BCD counter, so it stops at 9, right? 9 is the highest digit, so if I put in an A, it goes back to 0, B is again 1, and so on, right? And that's just because, you know, the number of clock pulses, and it overflows at 9, of course, because it's BCD. Yeah, so I'm very happy with my new PCB version here. So I have now produced 10 of these. So Frank and Manfred and Lilly, I'll send you one of the PCBs, and then you can have fun with that too and assemble it. And I'll also send you some bubble LED displays along. So the other components are fairly standard, and you should be able to source them easily, with the exception of the lens filter and the bubble LED display, which I'm sending along with the PCBs. And yeah, people were asking me, okay, so what's the practical value of this, right? I mean, you can, for example, use this as a pocket calculator, and I have a program here stored in the EEPROM. The calculator program is fairly long. I think I have it at slot number 1. So let's load that and let's run it. Oh, that's actually blackjack game. So I think I had it at slot number 2. Let's load it from slot number 2. Right, so that's the calculator program, right? So it's a 6-digit plus minus multiply divide calculator. So what's 1, 2, 3 plus 4, 5, 6 equals 1690 multiplied by 3 equals 5070, and I can also subtract 50, 80, and that should be minus 10. No, I think I added it. So let's subtract 10, 150, and it's 0, right? So yeah, pretty useful. Okay guys, so that's it. Thanks for watching.